In the previous section, we were looking at the definition of the derivative, and we said that it was the slope of the tangent line, so we needed to find a limit as h approached 0. And that definition is a little bit long, and sometimes the more complicated that our function gets, the more interesting that definition becomes to use. So what we're looking at here in chapter 3, the main purpose of this chapter is to come up with certain rules, what we would call shortcuts, to actually finding the derivative of a function. There is a certain notation that we're going to see that's going to pop up throughout the chapter, and it looks like this. It looks like d with a little line and then dx, so it looks like a fraction. What this is actually telling us to find is the change in the function value divided by the change in the value of x. So this is the change in y, so sometimes you would say dy dx. It's the change in y, or the function values. So how are the function values changing? How are the output values changing as the x values are changing? And this is basically the idea of slope. So when you see that notation, that's what that's looking for. It's the change in the function values divided by the change in the x values. And that's what we're going to find as the slope of the tangent line at any particular x value along the curve. All right. So rule number 1, all of these rules that we're looking at here are going to be kind of our simpler rules that we're going to kind of boil down to the idea of the power rule. Well, the first one here makes a lot of sense with what we've talked about. What if our function is a constant function? So for example 1, we have f of x equals -3. We want to know, how are the y values changing as the x values are changing? Well, when we have a constant function, f of x equals -3, I'm going to come up here and replace the f of x with what it really means. F of x is the same thing as y. We have y equals -3. This, if we were to graph this, this is a horizontal line, okay, at y equals -3. So let's just look at something for a second. If I choose any 2 points along this curve, so let's say I choose -1 comma -3 and 4 comma -3. For a horizontal line, the y values never change. So how are the y values changing as the x values change? Well, the y values actually aren't changing at all. So if I was to find slope, -3 minus -3, and 4 minus -1. So if I was to find the kind of the old-fashioned definition of slope here, we would end up doing -3 plus 3, which gives me 0, over -4 plus 1, or 4 plus 1, which is 5. So we end up 0 divided by 5 is 0. Essentially what we're saying is that there is no change in y. The y values are not changing at all. They're staying flat. So the y value is constantly -3. As the x values change, the y values don't change at all. So we would say that the slope of this line, the slope at any particular point along the curve, would always be 0. So we're going to say f prime of x, that's our notation that we're going to use to say derivative, would be 0. So essentially we're saying that at any x value that you choose, the slope of the tangent line is always 0. So this is a really important rule, pretty simple. Anytime we have a constant, we're taking the derivative of a constant. The derivative of a constant is always 0. The next rule that we're going to look at, a really important rule, is called the power rule. The power rule says that if we are taking the derivative of a function, where x is in the function and we have x raised to some power, so a pretty simple function, just x raised to a power. If we want to find the derivative, we have a two-step process for finding the derivative. The first thing that we're going to do, it says to take the power, take the exponent, and we're going to multiply that times the front of that term. So for example, let's look at example 2. If I wanted to find the derivative of this function, I would take the 5 and I would multiply it times the front of the term. So that would be 5 And then I'm going to write x to the power of. What I'm going to do then is I'm going to reduce the exponent by 1. In other words, we are going to subtract 1 from the exponent. So we multiply the existing power times the front, so multiply, and then reduce the power by 1. So if I was going to subtract 1 from this power, that would be 4. So the derivative of f of x equals x to the 5th will be f prime of x equals 5 times x to the 4th. So we multiply the power times the front of the term, and then we reduce that existing exponent by 1. Really important that we make sure that we write this notation, f prime of x. We want to make sure that we know that there's a difference between the original function and the formula for the slope of the tangent line function. Okay, so make sure that you write f prime of x. I'll be looking for that on your exams to show that that is different and what we're actually finding. So here's our next one. F of x equals x to the 7 over 4 power. So 7/4 power. All right, so I'm going to make note that I'm doing f prime of x. We're finding the derivative here. And we're going to multiply the power times the front. So that's 7/4, and that's going to become a big 7/4 out front of x, out front of that term. And then we're going to reduce the power by 1. Now we're going to be working with fractions a lot in this course. So if you need to brush up on your knowledge of fractions, you need to do that because fractions will be an essential part of this course. How do I subtract 1 from a fraction? Okay, so we have 7/4 minus 1. I recommend that you get fast at subtracting 1 from a fraction. So we're going to do kind of a long way here, then I'm going to just start going a little bit faster. So the first thing I want to do is think about both of them as fractions. So I'm going to think about 7/4 and then minus 1 over 1. In order to subtract fractions, I have to have a common denominator. What's really nice about subtracting 1 is that common denominator will always be what the other denominator is of the other fraction. So it's going to be 4. So what I really have now is 7/4 minus 4 over 4. And when we subtract fractions, we keep the common denominator, and then we combine the numerators on top. So 7 minus 4 gives me 3. So I get 3/4. So 3/4 becomes the new exponent. Okay, so here's my derivative, and this would tell me the slope of the tangent line at any x value along the curve. Alright, so the rest of the rules that we're going to look at in this section are kind of variations of the same. So what if I have a number already out front of the term? Then what do we do? If I already have a number out front of the term, then what I can do is I can just set aside that number and focus on just the part that has the x in it. So we can set aside the constant that's being multiplied out front and just take the derivative of the term, the part of the term that has the x raised to some power. So in other words here, if I was going to find the derivative, so I'm going to kind of use that notation really quick here. If I was going to find the derivative of both sides, what I can actually do is I can take the 3, that constant that's out front of that x to that power, and I can bring the 3 out front of that derivative notation. In other words, I can find the derivative just of this part right here, kind of setting aside that constant and focusing on the part that has the x. Okay, so if I was going to do that, what would it look like? Well, to find the derivative of x squared, I'm going to use my power rule. So that would be 2 times x, subtract 1 from the power, so 2 minus 1 is 1. Now what happens to that 3 out front? Well, the 3 out front is still there and gets multiplied times whatever comes after it. So here we have the derivative of our function f is equal to, bring the constant down, 3 times the power rule used on that x squared. So what we actually end up with then is f prime of x is equal to 3 times 2 is 6, and then x to the power of 1 is just x. So we get 6x. Now, is there an easier way to think about this? And the answer is yes. We usually shorten this process a little bit. So what we usually say is if you already have a constant out front that's being multiplied times that front of the term, we usually make this a little bit simpler and we just say take your power and multiply it times the front of the function. So that would be 3 times 2, which is just 6, and then we reduce the power by 1. So this process is a little bit faster than it initially appears. The key here is that the constant is not the focus. The derivative that we're looking at really is focusing on x itself. All right, so we're going to make this a little bit faster. We're going to use kind of this shortcut right here. So if I want to take the derivative of f of x equals 7 times x to the negative 12. So we're going to make note that we're taking the derivative here. And I'm going to take the negative 12 and I'm going to multiply it times the existing constant out front, because we know that's what's going to happen anyways. So 7 times negative 12, and you will be able to use a calculator on the test. So go ahead and type that into your calculator. We get negative 84. And why is it negative? Because we have a negative 12 times a positive 7. Okay, so we get a negative 84, and then we get x. Now we're going to reduce the power by 1. So we're going to subtract 1 from the existing power. Okay, be careful here. A lot of mistakes are made when we're talking about subtracting from negatives. When we talk about negative 12 minus 1, since they're both negative, then the number is going to stay negative and it's going to get more negative. So we get negative 13. Okay, if you want to, you can use your calculator there to take negative 12 and subtract 1. But just be really careful when you're subtracting 1 from a negative value. It gets more negative. It would not become negative 11. So be careful there. And also you can leave your answers with negative exponents. In this course we do not care if you leave your answer with negative exponents. All right, so let's look at a few more. For the next one here we want to find the derivative. All right, we already have that constant out front of 3/10, and I'm going to leave that constant just like that for a minute, and then we're going to focus on what happens when I bring the 10/3 down and multiply it times the front of the term. So that becomes a big 10/3 and then x, and then we're going to reduce the power by 1. So I'm going to think about that as 1 over 1. What is the fraction that I'm really going to be subtracting? Well, it's really going to be 10/3 minus 3 over 3, right? Okay, so we kind of see all the steps, everything that we've done so far. Now what's really nice here is that the constants now that are out front that are multiplied together, they're going to start canceling out, because 3 and 3 divided by 3 is 1, 10 divided by 10 is 1, so we end up actually with just 1. Those are reciprocals. And we multiply reciprocals together, we just get 1 times x, and then we end up with 10 minus 3 is 7. Keep the common denominator, we end up with 3. So the derivative of this function would be x to the 7/3 power. All right, so be careful with multiplying fractions. Make sure we know how to do that, and make sure we know how to subtract 1 from a fraction. Okay, another really important one here. I'm going to put a couple of stars here. When we're taking the derivative of a function, and we're going to use that power rule, oftentimes we want to rewrite the original function before we go and take the derivative. So this is really important. Okay, notice that the first thing that I'm going to do is not going to take the derivative. We have a radical, we have a square root. And if you go back to section 2.1, the very first section of the course, we talk about what a radical represents as an exponent. Okay, so this is really important. Okay, this is key to a lot of the problems that we're going to be doing. When we have square root of x, that is the same thing as x to the 1/2 power. The index of this radical is 2, the power on x is 1, so we put the power on top of the fraction and the index goes at the bottom of the fraction. Okay, if you need more refreshment, like I said, go back to section 2.1, the very first section. We review over what exponents represent as radicals. So notice that I have not taken the derivative. I have not taken a derivative. This does not say f prime of x. This is f of x equals 3 times x to the 1/2 power. all I've done is taken the original function and I've rewritten it, okay, in a more meaningful way for the power rule. Okay, so anytime you have radicals, the first thing that you want to do is you want to rewrite radicals as exponents. Okay, and it's not 3 to the 1/2 power, it's just x because the square root was applying to x, not the 3. So it's 3 times x to the 1/2 power. Okay, now I'm going to take the derivative. Okay, so f prime of x equals. So now we're going to do the same thing. I'm going to take the 1/2, take the exponent, and I'm going to multiply it by the 3. So that's 3 times 1/2, and I'm going to write it like this just for now so you can see all the steps. And then we have x, and then we're going to reduce the power by 1. Okay, so that really means that I'm going to be subtracting 2 over 2 because we have to give that common denominator. All right, now let's simplify a little bit. When we have 3 times 1/2, we're going to think about them both as fractions. And when we multiply fractions, we multiply across. So 3 times 1 is 3, 1 times 2 is 2. So we have 3/2 times x. And then from this right here, we're going to keep our common denominator of 2. 1 minus 2 is -1. So we get -1/2. So keep in mind that rewriting the original function so that we can use the power rule is not taking the derivative, but this is a really important step, and it's only after we use the power rule that we've actually officially used the derivative. So rewriting before you take the derivative is important. For our last example, we're going to look at kind of a little bit more complicated way of actually doing this, and then we're going to, from now on, we're going to make this a lot faster. So if I want to take the derivative here, so that's f prime of x equals. Right now, the existing exponent on x is 1. So if I do 1 times 5, we get 5, and then we have our power. I'm going to subtract 1 from the power, I get 0. Well, any base raised to the 0 power, really important, any base raised to 0 power is 1. So we essentially end up with that the derivative here is 5 times 1. Well, 5 times 1 is just 5. So when we have a constant times x, okay, so a constant times x, where x is being raised to the power of 1, the derivative will always be the number that's directly in front of x. Okay, and the question is why? So I don't want to have to go through that process every single time. There's a really easy explanation for why the derivative is 5. Let's go back to the idea of f of x equals 5x. This is the same thing as y equals 5x. If you think about this, this is like y equals mx plus b. What is the slope of this line? This is a line with a slope of 5. Lines have a constant slope, so at any x value along the curve, it doesn't matter what x value I pick, the slope of the tangent line will always be 5. Remember that essentially the derivative is the slope. Okay, so if anytime we have a line, we know what the slope is for every single x value along that line. So horizontal lines, we know they always have a slope of 0. This is not a horizontal line, but it's a slanted line, but it always has a constant slope of 5. Okay, so there's a good logical explanation for why. Okay, we're going to continue to use this exact same rule. We're just going to now apply it to several terms at a time. So if I want to take the derivative of a function that has more than one term, so notice this function has 4 terms. All I have to do is take the derivative of each term separately. So f prime of x, so remember I'm using that notation to say that this is different than the original function. I'm going to focus on one term at a time. So the first term, 3x to the 4th, we're going to use the power rule there. 4 times 3 is 12. We're going to reduce the power by 1, we get 3. Now I'm going to do the same thing with the second term. 3 times -5 gives me -15. Pull that out front, reduce the power by 1, so I get -15x squared. Okay, we're going to do the third term. 2 times 2 is 4. Reduce the power by 1. We end up with x to the first power. Now, once again, we want to be careful of something. This is a constant. What's the derivative of a constant? The derivative of a constant is always 0. All right, I'm going to make this look a little bit nicer. We usually don't write the 0. So I'm just going to get rid of that little last term there. And we usually don't put the exponent of 1. So this is actually kind of the simplified form of the derivative. So rule 4 here, the sum rule, says that if you have a bunch of terms added or subtracted, all you have to do is take the derivative of each individual term. So you can take the derivative of each term separately, and then the combined terms at the end will turn out to be the derivative of the entire function. All right, so let's do another one. This one has some fractions. Remember I said we need to get used to the idea of fractions. They're not going away. They will be a part of the rest of the course. Okay, f prime of x equals. So we're going to focus on one term at a time. So we're going to do 5 times, okay, this exponent is 4 divided by 3, so that's 4/3. So we're going to do 5 times 4/3. And for the sake of showing the steps, I'm just going to go ahead and write that out. 5 times 4/3 times x, and we're going to subtract 1 from the power. So that really means we're going to be subtracting 3/3. All right, let's go ahead and simplify that as we go. So that gives me, to think about this as 5/1, that gives me 20/3 times x to the 1/3 power. Okay, now we're going to focus on the next term. So I'm going to do this one in blue. So that's going to be -2/3 times, we're going to bring the power to the front, multiply it times the front, so that we're going to multiply by 3/2. And then we're going to do x, and we're going to subtract 1 from the power. So if I have 3/2 and I subtract 1, I really need to subtract 2/2. All right, so that gives me, let's simplify that. The 2's cancel, the 3's cancel, so I do with -1 times x to the 1/2 power. All right. And the rest of them are pretty easy. We don't have to do a lot of showing our work here. The next one is x squared. So we're going to multiply the 2 times the front, so that's 2. And we're going to write x, and we're going to reduce the power by 1, so that gives me 1. Okay, so this next one here is just -4 times x. Anytime we have a constant times x to the power of 1, the derivative would just be that constant. So we get -4. We're going to kind of get a little bit faster at those. And then the last one is a constant itself. There's no x. Okay, so be really careful here. Notice that there's no x here. This is just a constant. There is no x variable within that term. So that becomes +0. All right. So let's write down our final answer, simplified without all the extras. 20/3 times x to the 1/3 power minus, I'm just going to go ahead and write this as -x to the 1/2 power plus 2x minus 4, and we usually don't write the +0. So this would be the derivative of that entire function. So we can do one term at a time here. So we're using our power rule, kind of practicing our power rule for each individual term. All right, now the rest of the examples that we're going to be looking at are examples of when we would want to rewrite the existing function before we take the derivative. So it's really important that you realize that we have not taken a derivative yet until we've rewritten it. So we have to rewrite it, and then we're going to take the derivative. So be really careful about when we've actually taken the derivative. Okay, so we have f of r equals 4 divided by square root of r. So one of the big things is that we said that if you have a square root, if you have a radical, we want to rewrite the radical first. So I'm going to write this as 4 divided by r to the 1/2 power. Also, in order to use the power rule, we need the variable to be in the top of the fraction, not in the bottom of a fraction. So I need to move this term with the variable. I need to move this factor up to the top. When we do that, it gets multiplied times what's already there. So that becomes r. And remember that in order to move a base and its exponent to the top or bottom of the fraction. If I move it through the fraction bar, then the exponent changes sign. So this becomes 4 times r to the negative 1/2 power. So keep in mind something here. I have not taken a derivative. I have not used the power rule. All I've done so far is I have rewritten the existing function. So this is a rewrite. I'm not taking a derivative yet. Okay, really important that we understand the difference. This is exactly the same thing as what we started with. I have not taken a derivative. I have not used the power rule. Now we're going to use the power rule. So now I'm going to say f prime of r. So this is the derivative. Now I'm going to say negative 1/2 times 4. So that's 4 times negative 1/2. And then we're going to say times r, and then I'm going to reduce the existing power by 1. So I'm going to subtract 1, which really means I'm subtracting 2 over 2. All right. Remember that when I subtract 1, I have to have a common denominator, and that would be 2, so that's 2 over 2. So now let's simplify this. So now here's my derivative in simplified form. We'll think about this as 4 over 1. 2 goes into 4 2 times, so I end up with negative 2 times r to the negative 3/2 power. Okay. So really important that you can distinguish from rewriting the original function and actually taking the derivative of that function. Okay, so be careful there. All right, so number 12, we're going to do the same thing. The very first thing that I'm going to do is I'm going to rewrite. So I have not taken a derivative. This is f prime of t. All I'm going to do is we have these individual fractions. I have 3 individual fractions, and I'm going to bring the variable to the top so I can use the power rule. So that becomes t to the negative 4th power minus 3. I'm going to bring that up times t to the negative 3rd power. Okay, now that kind of covered that up. And then we're going to bring t to the top. And right now t has an exponent of 1, so it's going to become t to the negative 1 power. Okay, I'm going to erase these again so you can see. So for each one of these, what we've done is we've rewritten each one of these individual fractions by moving the variable to the top. And when we move it up, it gets multiplied times what's already there, and the exponent changes signs. Now that I've rewritten it in this convenient way, now I can use the power rule. So first of all, I'm going to make note that this is just a rewrite. Now I'm going to take the derivative. So that's f prime of t is equal to, and I'm going to get a little bit faster here. Negative 4 times 4, negative 16t. Subtract 1, we get negative 5. Remember, we want to be careful when our exponents are negative. We get more negative when we subtract 1. A negative 3 times a negative 3 becomes a positive 9, and then we get t to the negative 4 power. Negative 1 times positive 2 becomes a negative 2, and then we get t to the negative 2 power. And you can stop right there. We're going to leave our answer just in that form with all of the negative exponents. All right, this last example, just a straightforward taking the derivative. I'm going to show you 2 different ways to do this problem, and we need to be really careful about this particular one. First of all, we have a variable in the denominator, so we do want to bring it up to the top. Here's what you want to do to be careful about your rewrite here. Okay, if you decide to take x and multiply it, bring it up to the top, and change the exponent to be negative, you don't get to multiply just times the negative 10. You have to multiply times everything that's up at the top. Okay, so this is really important. Okay, you have to multiply this x to the negative 1 power times every term that's up at the top. You don't just get to apply it to the negative 10. You have to multiply times everything that's already there. So if this is the way that you choose to bring the x to the top to do the rewrite, then you have to do 6x cubed times x to the negative 1. So I'm going to add the exponent. So I get 6x squared. Because 3 and negative 1 give me a 2. So I'm adding the exponents. Okay. So remember, this is part of my rewrite. This is not a derivative yet. I have not taken the derivative. So when I do x to the negative 1 times 4x squared, that gives me 4x to the power of 1. And then plus 5. I'm going to add the exponents. X to the first power times x to the negative 1. That gives me x to the 0 power. And then I get negative 10. That's just a constant, so I'm just going to multiply in the x to the negative 1 power. Alright, so if I choose to do the rewrite that way, then this is what I end up with after I do the rewrite. So remember, x to the 0 power is just 1. 5 times 1 is 5. Then I end up with negative 10 times x to the negative 1 power. Okay, so far this is the rewrite. I have not taken a derivative yet, but now it's really easy to take the derivative. So now I'm going to say f prime of x equals, that would give me 12x for the first term. The next term would just be plus 4. The third term is a constant, so I get plus 0. And then the last term has that negative exponent that I need to be careful about. Negative 1 times a negative 10 would be a positive 10, and then we get x. Subtract 1 from the power, we get negative 2. All right, so if this is the way that I choose to do the rewrite, then this would be, in the end, what my derivative would look like. Is there another way that you can rewrite it? And the answer is yes. Another way that you can actually go about rewriting it, which will give us the same result, but might make a little bit more sense and be a little bit more easy for you, be a little easier, is to actually divide each of the terms in the top of the fraction by the x that is in the bottom. So let's say that we decide to do it that way. So let's say that I rewrite all the terms that are on the top. Okay, and I choose to rewrite this as 4 separate fractions, just like we did, kind of very similar to what we did in example 12, where we had those 3 separate fractions. If I choose to rewrite this, instead of having one big fraction, if I choose to rewrite it as 4 separate fractions, giving them back their own x as the denominator, now what I can do is I can actually reduce each fraction individually. Okay, you can think of it as bringing x to the top if you want to. I think it's just a little bit more straightforward just to reduce the fractions as they are. So we have 6x cubed divided by x. We'll subtract the exponents. We end up with 6x squared. Here we end up with 4x. The x's cancel here. I'm left with plus 5. And then nothing cancels in the last fraction, but I do need to go ahead and just bring that up to the top. So we get negative 10 x to the negative 1 power. So if you want to, you can rewrite it in this way. But we know what our answer will end up with in the end, whichever way we decide to rewrite it, whichever approach we choose to bring that variable in the denominator up to the numerator so that we can use the power rule. In the end, you'll end up with the same result for the rewrite, and then after you rewrite it, taking the power rule is pretty easy.